So we have this. Here's where we are. The total stress is equal to the stress due to the tension plus the stress due to... Naomi was probably late because she was at a protest. She was carrying her cello through a protest in case a jam broke out. So tension, bending moment, shear force, and okay, so we know how to deal with the first two of these. We don't know how to deal with the second two. Once we learn how to deal with the one for shear force, then we can do a lot of full problems. Like any beam, as long as it doesn't have torque applied to it, we can calculate full stress tensors for. So this is where we're trying to get to, is just finish shear force for today. So stress due to shear force. We'll try to get through this fast so you can get out there with the cool people and protest. Yeah. Hey, look at, I think that's a protest going by. I'm getting in on that. They should have done it with like a community college engineering teacher. Like, see, forget this class, I'm out of here. Yeah. I'm not really blonde. So what was the first thing I talked about when we did stress due to bending moment? What was the what? The track shape. Oh, I did it. Okay, before I did that might have been the first thing. Before I did that, I think I said what the restrictions are. We don't really have any restrictions on the stress due to tension and compression, but we did for bending moment. And there was a symmetry thing. You should look back at those. That's quizzy material. Yeah. But so here I'm going to do the same thing before we start shear force. Here are the beam requirements. Beam requirements. For the stress due to shear force. The math gets a lot more complicated because these relatively simple formulas come from those assumptions, and really in practice what you do is you do a numerical approach called finite elements. But what we're doing largely is just learning to interpret this stress information so that you know what it means, right? And you have ways to sort of sanity check your computer answers. So stress due to shear force. Right. Well, the stress due to tension and compression wasn't restrictive at all. There were no requirements. For bending, it was fairly restrictive. There was some symmetry stuff. There was some stuff about being prismatic. This is cripplingly restrictive. Very restrictive. Almost like that. So there are only two cross-sectional shapes we can deal with. Two cross-sectional shapes allowed. The first one is rectangular. Well, that's good. And even if you have a rectangular cross-section, the approximation gets bad as the thing's width gets bigger or its height gets smaller. So rectangular, and even this approximation is more accurate for height bigger than base. So if this is the height and this is the base, this is good. This, our results are bad. Okay, well, that's not real good news. The other news is, I don't know, it's more stuff you can do, but it's even more restrictive than rectangular shapes, is we can do circular cross sections. But we can only calculate the stress along the center line. Remember, that's where we put the z-axis because of the neutral axis. It all just has to do with the way that things like, it has to do with things that people have noticed about the deformation of certain shapes. They've done these experimental studies and they've made assumptions based on that, and those assumptions don't hold when you have a big base and a small height. And I couldn't go through the derivation right now. It takes a while to work through it and stuff. I don't have it at the top of my head, but that's what it is. The assumptions that we're making to come up with these equations hold for a rectangular shape like this, and they don't hold well for a rectangular shape like that. Okay, so, well, what good is this? Like, yes? Mm-hmm. Mm-hmm. You always, that's where you put the coordinate system, so it's always z. But you're right that it might not be, then it wouldn't be the middle up and down, but you would put the z-axis there. Yes? The z-axis is always the neutral axis because that's where you put your coordinate system. Yes, that's right. Yeah, well, let me go through the formula and then you'll see what goes into it and you can talk about it. But I know that kind of stuff is the hard part of wrapping your head well around this stuff, is just, oh, well, this, we looked at a picture on where we saw the XY plane and now we're looking at the YZ plane, and then, yes, it's complicated, but let me just go through the formula and then, okay, so does this even, so notice, does that even do us any good if we can only calculate the stress at the neutral axis for a circular cross section? Why even mention that? Well, the good news is that at least, so where on a cross section just generally do you have the biggest stress due to bending moment? Top and bottom, that's right, because it's as far away as you can get from the neutral axis. This is the opposite. The neutral axis is where you have the biggest stress due to shear force. So at least, ray of sunshine, silver lining, at least the neutral axis is where the stress due to shear force So in that sense, it is useful to be able to calculate it there. The neutral axis, yeah. All right, so before we do calculations, we need one mathematical preliminary. I'm just going to call it Q. Q. Really, mathematically, it's probably like the first moment of the area or something like that, but Q. And here's how you define Q. I think the easiest way to do it is just with a picture. So let's say Q with respect to line 1. So 1 refers to a line that's parallel to the z-axis. And here's what that means. So if you have some general cross-sectional shape, Q is still defined for a shape like this. It's just that the stresses that we got from the formula wouldn't be meaningful. And this has a neutral axis. So here's the neutral axis, and then that's also where we would put our z-axis. And let's define our line y1. Okay, so let's say this is y1. So that's the line parallel to the z-axis. That's our reference line. If you calculate the area above that line, we'll call that area A1. And the centroid of that area, you know, there's some centroid of that area A1. And you can figure out the distance from the neutral axis, that's the neutral axis, to the centroid. Call that D1. Then the value of this thing, Q, is equal to the area A1 times the distance D1. Okay, so you choose a line, calculate the area above that line, figure out where the centroid of that area is, and then multiply the area times the distance from the neutral axis to that centroid. It's, in words, it's complicated to say, but in that picture, it's pretty straightforward, I think. Q is just a mathematical thing we're going to use in our formula for stress. And this is a cool factoid. Cool factoid. Factoids are things that are like facts, but you're embarrassed thinking of them that way. So you call it a factoid? Possibly quizzy, yes. Yeah. They would go like on a quizoid. This cool factoid is, you know, you could also define this, you could just as easily define where you calculate, instead of calculating the area above this line, you calculate the area below and find the centroid of the area below, and then take the distance from the neutral axis to the centroid of the line below. What am I going to say? They're the same. Oh, yeah. That's like a magic show trick. Who would it? Right, exactly. So Q1, let's say above, is equal to Q1 below. That could pay your way, that bar trick could pay your way through undergrad. I guess it maybe depends where you go. Yeah, exactly. So if there's ever any reason that it's easier to calculate below, you can do that. Let's do an example. Exactly. This is in the formula for the stress due to no, that's not why. It's because it has to do with the way if you're looking at a cross section, you know, that cross section before the deformation is flat, and after the deformation, if you have a shape that's not a rectangle or a circle, actually, I think that's the torsion one. It's complicated. All that stuff, it just has to do, but okay, here's generally what I can say about these. It has to do with if you bend this thing and take careful measurements of how the things deform along all the axes, a lot of complicated interplay going on, right? For these two simple shapes, you can throw some of that stuff out just because of kind of lucky coincidence, you know. But fortunately, rectangles and circles are very common engineering shapes, you know. So we can get some useful information from them. Okay, well, I'm going to do an example right now. So let's say that this shape, it's a rectangular shape. That's 0.5 meters. And the height is 0.1 meter. Oh, no, 1 meter. That didn't make sense. And we want to calculate Q for a line that's 0.8 meters from the bottom. What's Q at this line? Yeah. So first what we have to do is we have to find the neutral axis. This is a rectangle, so the centroid is right in the middle. And so our coordinate system is like this. What? Did I draw it small? Oh, yeah. I mean, not everything is my fault. Okay. And so now that we've defined the neutral axis, the area we want is above this line. The centroid of this is in the middle here. Yeah, I know, it just keeps getting smaller and smaller. D goes from, I don't think it's getting any smaller now. That's D. So the area of that blue, the area of that blue area is 0.5 times 0.2. So 0.1 meter squared. That distance D, well, to go all the way from the neutral axis to the top would be 0.5, right? The centroid of this shape is 0.1 from the top. So this distance D is 0.4. You see that? So D is 0.4 meters. And so Q is 0.1 times 0.4 equals 0.04, and the units are meters cubed. Okay. So remember, the shapes that we're doing this for are simple shapes, so the geometry is not going to be complicated. And in fact, for a circle, we could just, I'm not going to do it for you, but you can do it if you want. There's actually just a formula in terms of the radius of this entire, well, you know, we'll talk about that. Okay. So, SI units for Q are meters cubed. And now we can translate that Q value into a formula for stress. So here is, draw this big, okay? There's going to be a lot of detail in this drawing. Okay, so here's a side view of the beam. What is it? It's not anything physically. The way it comes up is you go through this long derivation of the stress, and you have all these leftover terms that you lump together, and they have this semi-physical meaning that's Q. It's just mathematical stuff. Yeah, it's just mathematical stuff. So, okay, let's say that we have, our shear force is this, right? That's V. What kind of stresses does that produce? Well, think of a line of stress elements. So this is a whole row of stress elements. And stresses on those, so I'm going to, can you picture what I mean here? That's a whole row of stress elements. Stresses acting on those are in the same direction as the shear force. That makes sense, right? And because of the rules of shear stresses in stress elements, there have to be matching ones like this. Okay, so if our coordinate system is like this, which it will be, X is this way, Y is this way, Z is that way, then what element of stress is non-zero due to this shear force? So let me draw. Yeah, so let me take one of those and expand it. We're used to drawing stress elements with a different orientation, but so now we have X that way. Oh no, that's the way we always do it. Oh, that's great. Yes. Everything's turning around. Okay, so what stresses are non-zero? The middle ones? X, Y. Yes. Like this and like this. Do you see what I'm trying to draw there? So like this is a row of like 1, 2, 3. This is a row of 5 or whatever stress elements. And if you take one of them, it looks like that, because that's just the stress that it has to be in order to match that shear force. That's all. The hard part is picturing the orientation. If you can picture that, then reasoning is easy. It's just the same direction as the shear force. And so the non-zero stress due to V, the shear force, is the shear stress XY.
Always like
It's always XY in this case. With torsion, it'll be a little more complicated. And one more thing. Okay, so what I drew was a positive value of V, right? Because we have that funny sign convention, right? So if we have positive V, it's a force down like that. But that leads to, like, notice that's a negative XY shear stress. And so there's a negative sign, between the shear force and the shear stress. So now here's the formula. Tau xy is equal to negative shear force times Q divided by I, that's the area moment of inertia, times B. So V is shear force. Q is that thing we just did. I don't remember what it is. It's like a first, it's a first moment of an area somehow, but I really don't remember ever seeing a name for it. That's what we did. Yeah, that's right. I is the area moment of inertia. And B is the width of the cross section where the stress is being calculated. So if you're trying to calculate the stress like at the top, it's the thickness at the top. With a circle, since we can only calculate it in the middle, it's the entire diameter of the circle. All right, so let's do a full example. The thing is that now we can actually calculate the full stress tensor. So what? Yep, that's what we're going to do. Yeah. So let's say we have this beam. The mass is 100 kilograms. And it's 2 meters long. Small, please. And then we're going to calculate the stress at the midpoint. And then, we're using a coordinate system like this. Now we have to specify where in the cross section we're calculating it to. And so let's say the cross section is rectangular. It has a height of 0.1 meters and a width of 2 centimeters. And let's say we're trying to calculate the stress along this line. Okay. So we want stresses okay, so We want the stresses that are in the middle this way and along this line here. And the stresses all along this line are the same. Okay. Why did I choose that? I just had to choose something, so that's what I chose. Yeah, I mean, well, if I chose one where we're going to have non-zero values for all of the stress we can calculate. If I chose to calculate the stresses along the middle here, we wouldn't get any stress due to bending moment. Oh, yeah. And if I chose to do it at the top, we wouldn't get any stress due to shear stress, due to shear force, because, you know, what's the area above the top? It's 0, you know? Yeah. So I just chose something in the middle so these would all contribute. Yep. Do we need to know something about where that line is? It's at the midpoint. So this the second line. This is midpoint between the top and the middle. So this distance is 0.025. Yeah. Okay, so let's put a horizontal force on it too. So let's say that's 1,000 newtons. Since we're just calculating this at a single point, we don't have to do a general cut. We can just do a cut right at where we're interested. So at our cut, it's right at the midpoint. We have this force of 1,000. The total mass of the whole thing is 100 kilograms, so the force is 981. We have half of that weight on our piece, so you can think of this as a distributed load where over 1 meter we have 490.5. Right. So if we were going to do a range of points, we'd have this expressed as a function of x and then maybe a function of y if we wanted to go up and down, you know. So this is 490.5 newtons per meter. And then we have the internal loads, T, V, M. And now that we've chosen the piece to isolate, we can represent the weight as a point force. The length of this is 1 meter, so we have a total force of 490.5, acting at the midpoint. 1,000 there. T, V, M. Newton's second law says negative 1,000, 0. Plus 0, negative 490.5. Plus T, negative V is zeros. So T is 1,000. V is negative 490.5. And now the moment equation, the horizontal force doesn't produce a moment. What's the moment arm for this 490.5 force? The whole thing is 1, so this is half. This whole distance is 1. And then positive or negative? Negative. And then plus m minus vx is equal to 0. So m, what? Oh, v times 1. Thank you. So m is equal to 245.25 minus 490.5. So m is equal to negative 245.2. Why don't the derivative checks look like they work here? That's right. These are not functions of x, so you can't. Yep, they're just individual values. All right, so now one by one we can go through these stresses. So first, the stress due to tension. Sigma xx is equal to 1,000 divided by the area of that cross section, 0.002. And so that is 5 times 10 to the 5. Is that right? Okay, so the stress due to tension is 5 times 10 to the 5, and zeros everywhere else. And now we'll do the one for the bending moment. We have to calculate the area moment of inertia for this shape. For the shape of the cross section, yeah. So it's the base, 0.02, times the height cubed, 0.1 cubed, divided by 12. What do you get for that? Ooh, I bet I can do that. Nah, I don't want to. Okay. And what are the units? Yep. Good. And now the formula says the what element of stress are we going to get from this? XX, yep. So sigma XX is equal to negative bending moment times the coordinate where we're looking at it, the y coordinate, divided by I. So negative, what was m? So negative 245.25. And now the y value, we're looking along this line here. So the y value is positive 0.025. And then divided by the I we just calculated. And so what do you get for that? .68 times 10 to the 6. So the stress tensor due to bending is 3.68 times 10 to the 6, and zeros everywhere else. And then the last one is due to shear force. We need the Q. So Q is equal to the area above this line. So that's 0.02 times 0.025. What's that? That's 5 times 10 to the minus 4. Yeah. The area, okay, so Q is equal to 5 times 10 to the minus 4. That's the area. And then what's the distance from the neutral axis to the centroid of that area? So 0.025 to get to the bottom, and then another 0.0125 to get to the middle. So 0.0375. And can someone multiply those? Okay, minus 5. One thing to remember here is that that y in the bending moment, the stress due to the bending moment, can be plus or minus. That's a coordinate. The d in the Q formula is a distance. So that's an absolute value. Okay, so you can't ever get a negative value for Q. And now tau xy is equal to v, negative v. What was v? Negative 490.5. Times Q, 1.875 times 10 to the minus 5, divided by I that we calculated for bending, 1.6 repeating times 10 to the minus 6. Times the width at the place that we're calculating this, that's 0.02. Can someone calculate that one?
So it's not that. It's the entire base of the, not to the.
That's right. So I guess it matters, that distinction matters for the circular shape. The only other shape we have is a rectangle, and the base is the same no matter how high. But I was just saying it's the base wherever you're calculating it. So 2.765. Okay. Positive 2.76 times 10 to the 5. So the stress tensor due to shear force is 0. 2.76 times 10 to the 5, 0. 2.76 times 10 to the 5, 0, 0, 0, 0, 0. And so now, to get total, you just add up those three stress tensors. So the total stress tensor is equal to 5 times 10 to the 5 plus this, that gives 4.18 times 10 to the 6. .76 times 10 to the 5, 0. And if this was a brittle material and you were trying to figure out where it was going to break, what would you do with this information? It doesn't work as well for materials that stretch a lot, but works pretty well for brittle stuff. Well, before, so if you want to figure out if the material's in danger of breaking, now you would calculate the principal stresses, use that to calculate the maximum shear stress, and then you could compare that maximum shear stress to some measured value. So once you get to this, now you can go back and do all the things that we have done with stress tensors through the whole class. Right. Yeah. So next, find the principal stress, find the max shear. Yep. Any questions about that? Okay. Have a good weekend.